Hello, everyone. Have you ever wondered how your phone, your computer, or really any digital device actually works? Well, deep down, they are all speaking a secret language that's made of just two numbers, 0 and 1. In this explainer, we are going to learn how to translate that binary language into the decimal numbers we use every day. This skill is absolutely key to understanding how computers, how they think. So let's kick things off with a simple question. We all know how to count, right? But do we count in the same way a computer does? The answer is nope. And that fundamental difference is exactly why we need to learn how to convert between their system and ours. It all boils down to two different systems. We humans use what's called the decimal system or base 10. That's why we have 10 digits from 0 all the way to 9. Computers, on the other hand, use the binary system or base 2. They only have two digits, just 0 and 1. Why so simple? Because a computer's processor is filled with billions of tiny little switches that can either be off, which represents a 0, or on, which represents a 1. Literally, everything a computer does is built on this simple on or off language. Okay, so if we want to make sense of the data that's inside a computer, we have to learn how to speak its language, or at least learn how to translate its binary language into our familiar decimal language. And that translation process is exactly what we call conversion. So, what's the secret to doing this translation? Well, it's a really powerful idea called the positional notation method. Now, that might sound a bit complicated, but the idea itself is actually quite simple. It just means that the value of a digit depends completely on its position within a number. Think about it this way. You already use this method every day. Take the number 123. The 3 is in the units place, so it's just worth 3. The 2 is in the tens place, so it's worth 20. And the 1 is in the hundreds place, so it's worth 100. See, each position has a specific value. The binary system works the exact same way. But instead of using powers of 10 like ones, tens, hundreds, it uses powers of 2. Understanding this one idea is the key to everything else we're about to do. The good news is we can break this entire conversion process down into three very clear and simple steps. If you follow these three steps every single time, you will always find the correct answer. Let's take a look at what they are. First, we assign powers of 2 to every digit in the binary number, and we always start from the right with 2 to the power of 0. Second, we multiply each binary digit, each 1 or 0, by the power of 2 that we assign to it. And finally, for step 3, we just add all of those results together to get our final decimal number. It's a very reliable method. Alright, enough talk. Let's actually put this method into practice. We'll start with our first example, the binary number 1011. Let's apply our 3 steps. Okay, step 1, assigning the powers. For the number 1011, we start from the rightmost digit. That one gets the first position, which is 2 to the power of 0. Moving to the left, the next one is in the 2 to the power of 1 position. The 0 is in the 2 squared position. And the first one on the far left is in the 2 cubed position. Now for step 2, we are going to multiply each of those binary digits by the power of 2 we just assigned to its position. So that gives us an expression that looks like this: 1 times 2 to the power of 3 plus 0 times 2 to the power of 2, and so on for each digit. Before we multiply, let's make this easier for ourselves by figuring out what those powers of 2 actually are. 2 to the power of 3 is 8. 2 squared is 4. 2 to the power of 1 is just 2. And here is a very important rule to remember. Any number to the power of 0 is always 1. Don't forget that. Okay, now the multiplication is super easy. We get 8, 0, 2, and 1. And notice the really useful thing here. Any position that had a 0 in it simply becomes 0 in our final sum. This is a great shortcut that makes the calculation much easier. And now for our final step. We add those numbers together. 8 plus 0 plus 2 plus 1 gives us 11. And there we have it. The binary number 1011 is the same as the decimal number 11. See? Not so difficult once you know the steps. Excellent work on that first one. Now that you have the basic method down, let's try a slightly longer number just to reinforce the process. Let's convert 11010. Alright, here we go again. We are going to follow the exact same process. Step 1 is to assign our powers of 2 from right to left. We start with 2 to the power of 0 for the digit on the far right, and this time we go all the way up to 2 to the power of 4 for the digit on the far left. Okay, the positions are assigned. Now for step 2, let's write out our full expression, multiplying each binary digit by its matching power of 2, getting them all ready to be added together. And again, let's solve for those powers of 2 first to keep our work neat. 2 to the power of 4 is 16. 2 cubed is 8. 2 squared is 4. 2 to the power of 1 is 2. And of course, 2 to the power of 0 is 1. Now we can perform the multiplications. And just like we saw before, the positions that had a 0 in them simply become 0, which leaves us with a very simple addition to do, just 16 plus 8 plus 2. When we add them all up, we get 26. So the binary number 11010 is equal to the decimal number 26. As you can see, the method works no matter how long the binary number is. You have now successfully converted two different binary numbers to decimal. So before we finish, let's quickly summarize the most important points that you need to remember. Let's recap. First, always remember that binary is a base 2 system, which is why we always use powers of 2. Second, position is power. The value of any digit depends entirely on where it is. Third, you must always start from the right with a 2 to the power of 0 position. And finally, you just need to multiply each digit by its place value and then add everything together. That's the core of it. So you now have the skill to translate a computer's language into our own. But that leads to a new and interesting question. How would you do the reverse? How could you take a regular decimal number, like your age for example, and convert it into binary for a computer to understand? That is something to think about for next time. Thank you for following along.